You may hear some background noise in today's episode. Drills, hammers, and maybe a bit of shouting. But that's not a sound effect. It's real construction happening just outside my studio. But instead of letting it derail our day, let's run with it, because today's Flashcard Friday's episode is all about the history of construction. The math, the science, and the literal sound of building through time. But first, a quick word from my advertisers. Welcome to Math Science History, where every Friday we break down one big idea into a few minutes or less. I'm Gabrielle Burchak, and today we are traveling from the Renaissance domes of Brunelleschi to the steel skeletons of modern skyscrapers. So, what does math have to do with it? Imagine trying to build something. A home, a temple, a bridge without measurements. No rulers, no angles, no formulas. Well, that's kind of how we began. But even the earliest builders observed nature, the way trees branched, how beehives tessellated. Over time, we turned these observations into rules, and those rules became geometry. The word geometry itself means earth measure. Early construction in Mesopotamia and Egypt depended on geometric knowledge for everything, from irrigation channels to massive pyramid alignments. Ancient engineers didn't just use intuition, they used proportional systems, grids, and trigonometric rules, like the Pythagorean theorem. Speaking of the Pythagorean theorem, let's talk triangles, specifically the 3-4-5 triangle. In ancient Egypt, builders used knotted ropes divided into 12 units to create right angles. Stretch it into a triangle with sides of 3, 4, and 5 units, and voila, a 90-degree angle. This Pythagorean triple predates Pythagoras himself, as some people don't know. But he did capitalize on it, so good for him, right? The Pyramid of Khufu, also known as the Great Pyramid, wasn't just a pile of stones. Its base is almost perfectly square and aligned with cardinal points. That required surveying, astronomical alignment, and, you guessed it, math. So while construction workers hammered away under the desert sun, scribes and architects used calculations we now call trigonometry. So let's fast forward to ancient Rome, where the Romans took it up a notch. Love these puns. So this was where construction and engineering exploded with innovation. We had roads, aqueducts, amphitheaters, and bathhouses, all thanks to Roman mastery of concrete, arches, and applied geometry. Take the Pantheon, for instance, a concrete dome that's nearly 2,000 years old. Its oculus, or open eye in the center, reduces weight while providing natural light. The dome's thickness tapers gradually, a brilliant solution for weight distribution and a marvel of engineering. Vitruvius, a Roman architect and military engineer, wrote De Architectura, a treatise on proportion, geometry, and symmetry in buildings. His work influenced architecture well into the Renaissance and beyond. Construction was no longer just stacking bricks. It was engineering based on math, philosophy, and aesthetics. So now we move on to Florence in early 1400s. The city had a problem. A massive cathedral needed a dome, but it was too wide for wooden scaffolding. Nobody knew how to build it. Enter Filippo Brunelleschi, a goldsmith with a mind for mathematics and a stubborn streak. Inspired by Roman techniques, Brunelleschi studied geometry, physics, and mechanics. He designed a double-shelled dome with a herringbone brick pattern that locked the structure into place. There was no scaffolding needed. He even invented new machines to hoist materials. This wasn't just a dome. It was a blueprint revolution. He applied mathematical models, used linear perspective to draft 3D plans, and proved that art, science, and construction could be one and the same. If you've ever wondered what a mathematical renaissance sounds like, it might have even been the rhythmic clinking of bricks being laid into a dome that defied the odds. So while Florence marveled at domes, The Islamic world was flourishing with mathematical architecture of its own. Islamic builders developed complex geometric patterns, or giri, as well as 3D stalactite-like vaults known as muqarnas. They weren't just aesthetic. They were based on algebra, symmetry, and combinatorics, often with no repeating pattern, hundreds of years before Penrose tilings. It's so cool. In Iran and Central Asia, architects employed spherical geometry to construct domes that transitioned seamlessly from square rooms below. So let's jump to the 1800s, when iron and steel changed everything. Structures could now go higher, stronger, and more complex. With the Industrial Revolution, math evolved to meet the challenge. It always does. We had material science, tensile strength, load distribution, and modular construction. The Eiffel Tower in 1889 was criticized for being hideous, but it showcased the power of math and iron. A lattice of curves and crossbeams calculated to withstand wind forces. As buildings grew taller, engineers needed to calculate how much force a beam could take before bending. That required calculus, physics, and something called finite element analysis. It was a numerical method that breaks down structures into small parts to analyze stress and strain. And with these changes come new sounds. Rivet guns, steam hammers, and cranes reshaped the construction soundtrack of the world. Now I'm going to move on to today's modern marvels and the math behind skyscrapers. Today's skyscrapers are feats of math and material. Consider the Burj Khalifa, currently the tallest building in the world. It had to withstand both gravity and wind vortices, requiring simulations and algorithms grounded in physics and fluid dynamics. Architects use software like CAD and Revit, but under the hood, it is all math, from parametric equations for curves to vector analysis for wind loads. Even acoustics are modeled in modern construction. Want a concert hall with perfect sound distribution? That's wave theory, reflection modeling, and geometric diffusion. And construction itself has become a science, using robotics, 3D printing, and AI to predict structural weaknesses or cost overruns before they happen. So, if you pause and listen, construction still echoes the past. The steady beat of a hammer, it mirrors the rhythmic pounding of stones in ancient quarry work. The creak of scaffolding and buzz of a crane, that echoes of Roman pulley systems and Brunelleschi's ox-powered hoists. The hum of machinery, the Industrial Revolution reimagined. Construction is noisy, but it's alive. It's a conversation between math and matter. Every clang, thud, and drill is part of a dialogue that began thousands of years ago, one that continues with every new building and bridge. So today, if you hear the sound of construction in the background, don't tune it out. That's the sound of applied geometry, the sound of ideas becoming tangible. That's the sound of history still in motion. So, what can we take away from today's Flashcard Fridays? Well, math is in every brick. From ancient Egypt to the Burj Khalifa, construction relies on geometry, algebra, and physics. Next, architectural revolutions shape societies. Innovations like Brunelleschi's dome or iron bridges changed not just cities, but world views. And finally, construction noise is a living legacy. It reminds us that science and math are not silent disciplines. They are audible in every step of progress. So that's it for today's Flashcards Friday. And if you like this episode, be sure to subscribe, share, and leave a review. And maybe take a walk around your neighborhood. Listen closely. You just might hear the math. As for me, I'm hearing it and I'm hearing the math. I find it absolutely exciting. So until next time, carpe diem, my friends.